Alright, so the question here is asking how many of these molecules are polar. So we have sulfur trioxide, oxygen difluoride, beryllium chloride, carbon tetrachloride, O3 or trioxide, or even ozone if you will. So the way we answer this question is drawing its Lewis structure, determining the molecular geometry, and then determining the net dipole. From that net dipole, we can find out whether it's nonpolar or polar by seeing that if all the domains are the same and there are no non-bonding pairs of electrons, it will be nonpolar. If there are diverse domains with non-bonding pairs of electrons, it will be polar. Now, there are special cases when the non-bonding pairs of electrons will cancel, leaving a nonpolar molecule, but those are special cases, and we will see if those come up or not in these problems. So first up, we have sulfur trioxide. Sulfur trioxide has 24 valence electrons. When we first draw its Lewis structure, we realize that the sulfur atom is left without an octet, violating the octet rule. So we have to make a double bond here, here, or here, telling us that the molecule has resonance. And then so this is what the Lewis structure actually looks like. It has a domain geometry of trigonal planar, also a molecular geometry of trigonal planar, and its bond angle is 120 degrees. So the S atom is going to have a partial positive charge, and each oxygen atom will have a partial negative charge, thus canceling and leaving a nonpolar molecule. Next up, we have oxygen difluoride. So oxygen difluoride has 20 valence electrons, and this is what its Lewis structure looks like. Now don't be fooled, you might think this might be a linear molecule, but it's not. It's actually a bent molecule. Because its domain geometry is tetrahedral, its molecular geometry is bent, thus leaving a bond angle of a little bit less than 109.5 degrees. There is a partial positive charge on oxygen, a partial negative charge on each fluorine atom, thus making it a polar atom because of the two non-bonding pairs of electrons. Next up is beryllium chloride. Beryllium chloride has 16 valence electrons. Its Lewis structure looks like so. And you might think, why doesn't it have a full octet rule? It's because beryllium is an exception, and there are no resonance structures for this. So it's going to be a linear domain geometry, a linear molecular geometry, having a bond angle of 180 degrees. So there's going to be a partial positive charge on the beryllium atom, a partial negative charge on the chlorine atom, and a partial negative charge on the other chlorine atom, thus canceling with the net dipole, leaving a nonpolar molecule. Next up is carbon tetrachloride, and it has 32 valence electrons. Its Lewis structure looks like so, having a full octet on every single atom, and its domain geometry is tetrahedral, so is its molecular geometry is tetrahedral, having a bond angle of 109.5 degrees. So this is what the molecule actually looks like. It has a partial positive charge on carbon, a partial negative charge on chlorine, another partial negative charge on chlorine, so on and so forth, having 4 partial negative charges on each of the chlorine atoms, thus having the same domain geometry and molecular geometry, able to cancel the net dipole, leaving this molecule to be nonpolar as well. Next we have O3, trioxide, or ozone if you will. This molecule has 18 electrons. Its Lewis structure looks like this, but the middle oxygen atom does not fully have a full octet, so it violates the octet rule. So it has to have a bond angle here, double bond angle here, or a double bond angle here, thus telling us it has resonance. So its new Lewis structure looks like this, but it has a domain geometry of trigonal planar, but its molecular geometry is bent, having a bond angle of less than 120 degrees. So this is what the molecule actually looks like, having the non-bonding pair of electrons here on this oxygen atom, with that oxygen atom having a partial positive charge, and then having a partial negative charge on the two other pairs of oxygen atoms, thus unable to cancel the net dipole, leaving a polar molecule. Alright, let's recap. So sulfur trioxide has a domain geometry of trigonal planar, a molecular geometry of trigonal planar, thus being able to cancel the partial negative dipoles on the oxygen atoms. Next we have oxygen difluoride. Oxygen difluoride has a domain geometry of tetrahedral, but its molecular geometry is bent, therefore unable to cancel the net dipoles, leaving a polar molecule. Then we have beryllium chloride. Beryllium chloride has a domain geometry that is linear. Its molecular geometry is also linear, thus being able to cancel the net dipoles, leaving a non-polar molecule. Then we have carbon tetrachloride. Carbon tetrachloride has a tetrahedral domain geometry along with a molecular geometry that is tetrahedral, thus being able to cancel the net dipoles, also leaving another non-polar molecule. Lastly, we have O3, ozone trioxide, and it has a domain geometry that is trigonal planar or a molecular geometry that is bent, thus leaving it unable to cancel the net dipoles, leaving a polar molecule. Finally, some common mistakes. One common mistake you can make is misplacing the electronegativity values. So for chlorine, we know that chlorine has a higher electronegative charge than carbon, but make sure you don't make the mistake of having the dipole go towards carbon, because the dipole will always go towards the more electronegative atom. Another common mistake is ignoring the non-bonding pairs of electrons. So for oxygen here, if you just saw that you had 3 domains and you instantly thought trigonal planar and said that it net dipoles cancel, no, because the non-bonding pair of electrons here would leave this molecule to be actually bent and unable to cancel those dipoles.